Okay, welcome everybody to representation theory. I've had a couple of comments that it might be a bit weird to give a lecture on representation theory and tell the people beforehand to brush up on their representation theory, but I hope it will make sense in the end. Yeah, the thing about representation theory is that it's a sort of quite nebulous thing. Like, I think I've had 5 or 6 courses so far that at some point talk about representations, but it's always different objects and whatever. So when you hear representation theory, you might think about groups, be they like finite or Lie or whatever other kind of group you might think of. Or I don't know if you have done quantum field theory or advanced quantum field theory, ℂ-algebras. Or if you've done topology in physics, Clifford algebras. Or if you've done any of Raf's special courses, maybe quivers. And like there's a lot of different kinds of objects that can sort of be represented or that have some sort of representation theory around them. And they all sort of use similar language, but yeah, I don't know. So my first goal is to unify all of this, bring it all together, namely by talking about the representation theory of associative C algebras. Because, well, Clifford algebras are associative algebras, so that's nice. Groups can be associated in algebra with them. Lie algebras, quivers can all be formulated in terms of algebras. So what is this thing we are talking about? What is an algebra? And yeah, an associative algebra, or let's say C algebra, is a C vector space or a complex vector space with an additional operation V together with a bilinear operation multiplication, which we just represent by juxtaposition. We want it to be bilinear, so yeah, like if you multiply with a scalar here or there, that should carry on to the result. But we want one more thing, namely we want this thing to be, well, associative. So for every U, V, W in V, we want UVW equal to UVW. Well, okay, would have been, might have been expected. And one more thing, we call an associative algebra unital. If it has a 1 element. So if there is an element called 1, such that, well, this thing behaves like we would expect a 1 to behave. 1 times x is equal to x times 1 is equal to x. Yeah, in other words, we could say an associative C algebra is a ring that contains C in its center. And examples. Yeah, this is sort of where the fun begins. why are we even talking about that? Well, the simplest example, C itself, with the multiplication we expect. Okay. Not a big stretch, I believe. Second thing, the polynomial ring in one indeterminate, with multiplication just being multiplication of polynomials. If G is a group, we can define C adjoint G, the group algebra, to be, well, formal linear combinations formal linear combinations of elements of G. So we have complex coefficients and then just elements of the group. We can equip this thing with a multiplication just by saying that AIGI multiplied by sum over J, BJ, HJ is equal to, well, the double sum, where we multiply the coefficients and we multiply the elements of the group inside the group. And this thing is also a C algebra. Then is a group, it's a C algebra, and it also has a unit, or yeah, a one. Namely 1 times the neutral element of the group. Now the word group algebra can actually refer to a lot of things when you're not strictly talking about the field of algebra, but like when you're talking about functional analysis, operator algebras, Lie groups, then you could also mean other things when you say group algebras. For example, if G is a topological group, then we could think about MG, which is the regular complex measures. And we can define some sort of convolution of measures. And this forms again an algebra. Equipped with and it again has a unit, namely the Dirac measure at the neutral element. And similarly, we can do like other stuff, like if we have a locally compact group, then we can do L1 with respect to some H measure, and again the convolution. Or if we have a Lie group, we could do distributions with convolution, and well, we could do compactly supported measures, we could do compactly supported continuous functions, compactly supported smooth functions, compactly supported distributions, whatever. There's a whole lot of things that we could also reasonably define as group algebras, and they sort of encode the extra information we have about the group. So if we look at the measures, we have a topological structure. These measures sort of encode that the group is also topological. For L1, we have the R measure and therefore some local compactness. Distributions encode the differential structure on a Lie group. And well, these compactly supported versions all do similar things, but have the advantage that sort of integrals turn out to be finite. But that's more or less just a side note for the functional analysts among us. Next thing, if G is a Lie algebra, then we can define what's called the universal enveloping algebra. Define U of G to be, now we start the fun. It is sort of the most general algebra that we can embed G into, such that the Lie bracket can be expressed as a commutator. How we construct this is we take the tensor algebra, which just means that we take a formal direct sum of like the 0th power of G with the 1st power of G with the 2nd power of G, and so on. Sort of, we just adjoin formal products that are by definition multilinear. And then we divide all of this by some relations, namely that, well, the commutator should be equal to the commutator should be equal to the Lie bracket. And this is sort of a formal hack. We will see a bit how these algebras look a bit later on.
What do you exactly mean by division here?
Taking the quotient, sort of, we consider these objects to be 0, or in other words, I mean, I've not written this properly. This would be the proper way to write it. We consider this object here to be 0. What this means is we sort of take this formal stuff, but we consider this thing here and this thing here to be the same. So in other words, we just take whatever external powers of G, add them to each other, and then we say, well, but the Lie brackets should still be the same as the commutator.
But wouldn't that hold true, like, anyways?
No.
Okay.
Because, like, those are just elements of this tensor product, and this tensor product isn't symmetric or anything. Yeah, it's called the universal enveloping algebra, and it has the sort of the property that for every Lie algebra homomorphism, from G into, for example, some endomorphism ring, can be extended uniquely to a homomorphism of commutative algebra, of associative algebras of UG to that same endomorphism ring, just by saying that multiplication should map to multiplication, and then therefore the Lie bracket should be the commutator, which is the reasonable thing to suppose here.
I'm sorry, I also have a question. It's about the group algebra.
Yep.
So normally I'm only used to the fact that group elements can be multiplied, but you said that an algebra is a vector space.
Yes.
How does addition work?
Addition works just by adding the coefficients. So you have, like, I don't know, if G1 and G2 are elements of your group, then you can have like 5G1 plus 3G2 would be an element of that algebra.
Okay, you cannot simplify it. All right.
And yeah, you cannot simplify it. And if you add 7G1 plus 4G2 to that, that would then just be 12G1 plus 7G2.
Yeah, that looks very much just like the polynomial algebra.
Yeah, with the one caveat that if you multiply them, you actually multiply the elements in the group. But
yeah, of course.
Yeah, but yeah, it's basically the same as polynomial rings. Yeah. Yeah, and one sort of very important caveat is about the universal enveloping algebra. It is not just any algebra that sort of contains the Lie algebra as a subset. It is the most general one. So if, for example, you have, which is usually the norm, if you have a Lie algebra that is already subset of some matrix ring, so if G is the subset of and V, think of the classical Lie algebras, SLN subset of and R to the N, whatever UN, subset of and C to the N, I suppose, and so on. Then UG is much bigger. Than just NV. And it is, in fact, usually infinite dimensional, which you can already see by the fact that sort of this summand has dimension 1, this summand has dimension dim g, this thing has dimension dim g squared, dimension g to the 3rd, dimension g to the 5th, and so on. And dividing out this ideal reduces the dimensions somewhat, but not by very much. And this, I guess this notion can also be made a bit more exact a bit later. Or, I don't know. And yeah, one sort of important thing we also are going to talk about. Oof, why is this even important? Well, okay. So if you're talking about rings, at some point somebody is going to come along and ask about ideals. So better do this one quickly now. If we have a C algebra called R, and we have a subset called I, and this thing is called an ideal, or more precisely, a left ideal. If the following two things hold, firstly, for all, yeah, it's sort of closed under the usual group operations. You can just say that for two elements in I, their difference should also be in I. This sort of encodes that addition and inverses should be contained in I, so it should be a subgroup. And secondly, and this is the strong condition, for every A in R and every B in I, the product should also be contained in I. And the fact that this thing is a left ideal is encoded in the fact that here we can multiply on the left by any element in our algebra, and the right element has to be an I. Yeah, I don't know, left, because we want R times I to be a subset of I, and the set when we exchange those two doesn't necessarily have to be contained in I. And examples, well, I don't know, if we look, for example, for this doesn't necessarily fall under the definitions we have here, but usually the integers are a very nice example of a ring. And then you have the ideal 2z of the even numbers, or 3z of the numbers divisible by 3, 5z, or I don't know, even 4z. Those things are ideals. Because if you have a number divisible by 2 and you multiply it by any other integer, then that number is still divisible by 2. And this is a very important thing that we wouldn't have in fields, because in fields everything is just always divisible by everything else except for 0. So this is something native to rings. And generally, if R is our left, is an algebra, then, and X is some element, then Rx, or like the set of objects of the form A times X for A in R, this thing is a left ideal called the principal ideal. Generated by by X, sorry. And we will write it as X within these ideal brackets. And then similarly, if we have a family of ideals, then there's some the direct sum is also a left ideal. Oh yeah, one small thing I should mention. Since we are not only talking about rings but also about C algebras, this condition here especially then implies that it's also a subspace, a vector subspace. So we are talking about.
I have a question. At the definition of the ideal,
yeah,
you wrote that I is a subset of A, but shouldn't that be R? Yeah.
R, yeah.
Okay, yes.
Huh. Interesting. Also wrote that wrong in my lecture notes, but yeah, thanks. It should of course be an R. So not only are we talking about subvector spaces, they should also be invariant under multiplication on the left with any other element in the ring or in the algebra. and this direct sum that we've defined here is just, well, those elements in R that can be written as a finite linear combination of elements in these ideals. So X can be written as x1 plus xn, where xi is contained in, well, every xi is contained in one of these ideals here. And, well, if those things here are principal ideals, then there's also a special kind of notation for the sum of the I alpha, namely it's just yeah, funny. Where capital A is the index set for our indices. So if we have finitely many, we can, for example, write our ideals like this. And that would just be the elements that can be written as a finite linear combination of these xi. And now for the, I guess, more central definition. Yeah, again, we have a C algebra, and then the left module is a C vector space. V equipped with a map from R times V to V, which we will again just denote by multiplication or by juxtaposition, I guess. Such that three laws are satisfied, namely, we want this to be sort of associative. So if we multiply within the algebra first and then multiply with an element in the module, then this should be the same as first multiplying with the module and then multiplying within the module again. Secondly, we want this to be distributive.
Wait, I'm very confused. The R here is a ring, right?
Yeah.
Okay. Yeah.
Or C algebra. Yeah. Second axiom is we want this to be distributive, and I guess we also want it to be distributive in the second argument. So this means nothing but that this R acts by linear maps or by means of linear maps. And this is already starting to sound a bit like a representation, because you basically map R to end V, to the endomorphisms on V, which is exactly what a representation does. And thirdly, well, if we have a 1, then it acts trivially. Okay, alternatively, we could just say that this map, which we could call mu, is a ring homomorphism from R to the endomorphism ring on V. Yeah, that should encode all of the axioms. And to be sort of in spirit with the last lecture I gave, I just introduced a new kind of object. So what are the morphisms? An R linear map. Between two R modules. Is an an R module homomorphism, is a linear map, a C linear map, such that for all elements in R and all elements in the module, it respects the multiplications, meaning exactly this, this property here. Yeah, generally modules are a generalization of vector spaces. When we don't have that C vector structure here, or like if you forget that an R module is by definition also a C vector space, those are exactly the same axioms you have for a vector space, with the difference that your R is just is a ring and not a field in itself. So modules have a bit of ugliness, or I don't know if ugliness is the correct word, but there are some nice properties that vector spaces have that modules don't have. And for example, the existence of a basis. And I guess this is, on the other hand, also what makes modules a much more rich structure, which we can use to express more things. And one last comment, yeah, the left R modules, together with the R linear maps, they form a category. Now for the all-important examples. What do these modules have to do with representation theory?
Just a brief question. Like I understand endomorphisms, but what exactly happens in an endomorphism ring?
The endomorphism ring is the vector space of linear maps, and their multiplication is just composition. So think of square matrices.
Okay.
And you can add them and you can multiply them. And then they form an algebra.
Okay.
So, and yeah, I mean, I guess here's the mathematician again, coming for the most obvious example or the most trivial example. R itself is an R module. So is every ideal of R. Because if you look back, have an ideal, okay, that is here a subgroup, and if we plug in just elements of C in this for our A, we get that it's a vector subspace. or a vector space. And then this property just tells us that sort of our group operation, we can restrict it to I, and it's still closed. And obviously, since it was an algebra to begin with, we still have the associativity and the fact that one acts trivially if it exists, and so on. Then next example, well, if you have a bunch of R modules, then we can take the direct sum. What is this direct sum? The direct sum consists of those x in the product or the Cartesian product of all of them, such that x alpha is not 0 for only finitely many alpha. So that in effect, every element of this direct sum can be written as the formal linear combination of elements of the M alpha. Note that we can't use a simple argument as we used for the definition of the sum of ideals, just because we don't have some overlying module that they are all part of.
I'm sorry, I don't understand this sort of double index notation. You wrote M of alpha and then brackets and then again alpha. What does it mean?
Yeah, M alpha for alpha in some index set A.
Oh, okay.
It's just notation for like a family indexed by some set. Okay. And I guess if we can have modules, we can also have submodules. Yeah, again, R is a C algebra. An R module M is called a submodule. Of another R module N. If, well, I guess it's kind of obvious. So if just the obvious condition sort of, if, well, firstly, it's a subset. And secondly, if all of the operations are just obtained by restriction. If sort of, yeah, how did I write this here? Yeah, another way to phrase this is we just have a subset, and if that subset is closed under left multiplication with elements of R, and also under addition, then it's a submodule. I guess I went for the straight algebra way of how to define this. I guess the second one is the more tangible one. So yeah, there's a lot of different terminology. When you're talking about representation theory, you're usually not going to call it modules and submodules. You're going to call it representations and sub-representations, but it's the same thing. And well, secondly, an R module M is called simple. In the representation theory language, you would say irreducible. If 0 or the trivial R module and M are its only submodules. So
you mean irreducible, right?
Yes, exactly the same notion. Yeah, if it's not simple, it's called reducible. If M is not simple, it's reducible. And one last notion, and I guess the veterans of group theory are already seeing this coming. An R module M is called decomposable. Or I guess completely reducible. If you can write it as the direct sum of simple modules. Or in other words, a representation is decomposable if you can write it as the direct sum of irreducibles, which, yeah, I don't know, in most practical cases is the case. Yeah, and I guess one remark I could make is the fact that left ideals are just submodules of the R module R. And yeah, one last definition. Which sort of goes back to what Srinivas, I think, asked. Let M be left R module and N a submodule. Then we define the quotient of M by N to be the sets of equivalence classes modulo N. So what you're doing is you take the subspace X and you add one element, you add X to every element in there, and what you get is, well, it's not a subspace, not a subvector space, but it's a sub-affine space, I guess. And those things are the elements of M modulo N. This has the effect of saying that every element in N is basically treated as 0, because if X minus Y is contained in N, then X plus N is equal to Y plus N. just because it is equal to x minus y plus n. But this thing is contained in n, so adding it to n doesn't change anything. Yeah, I guess so. And yeah, so m modulo n is called the quotient. Of m by n. And it can also be turned into an R module as an R module by having a times x plus n, defining that thing to just be a times x plus n for a and R and x and m. And I guess one very important remark is that modules of the shape are modulo semi-ideal because R is an R module, I is an R submodule, so this thing is a well-defined R module, are very important for the task of classifying and whatever the modules, because of a very simple fact, or I don't know if it's very simple, but so because if M is a if we have an R module M, then this module is simple if and only if it is cyclic. So, i.e., it is generated by one element. The reason being, if M is simple, then we can just take an element and let's say it should not be 0. Then we can consider just everything we get if we multiply our element by every element in R. This thing is a submodule. And since V is not equal to 0, we have V is equal to 1 times V is an element of RV. So this thing can in particular not be 0. So then RV has to be all of M because M was supposed to be simple. And the other way around should also work. This is sort of akin to having, I don't know, in topology, you can have irreducible spaces. And at some point you prove that a space is irreducible if and only if it is the closure of a single point. Yeah. So, yeah, in generally in representation theory, we are looking for two things. Well, one thing is every module decomposable. Can we write any module as the direct sum of simple modules? And secondly, what do the simple modules look like? We've just seen that every simple module is cyclic or a module is simple if and only if it is cyclic. But this means, yeah, by definition, that there is an element V such that M is equal to RV. But this means that M is somehow isomorphic to R divided by the annihilator ideal of the element V. Where the annihilator is just all of the elements in R such that A times V is equal to 0. So this means every simple module can be written as R divided by some ideal. So that is why I've talked about this, even though I guess quotients aren't usually mentioned in representation theory. But now, why did I introduce modules, and why did I say that modules were the same thing as representations? So what are examples of modules? And the first thing is, again, well, okay, we just take the trivial example of our C algebra being C itself. Then our modules are just vector spaces, and that's it. What is an example of a C vector space? A simple R module? Well, you can always find subspaces, except when your vector space is one-dimensional. So simple R modules are just one-dimensional C vector spaces. So I guess they are isomorphic to C itself. And also you can sort of decompose every C vector space into a direct sum of C's, since every C vector space has a basis. There is an index set such that we can write our vector space V just as the direct sum of C. So in particular, every reducible C vector space is decomposable. Or I guess every C vector space or R module is decomposable. Okay, boring example. Oh shit, my laptop needs a bit more power. Be back in a sec. Okay, next example, much more interesting. The polynomial ring in one element. Well, this thing is generated by exactly one element. Generated over C as one by the element X. And in particular, sort of a C module, an R module structure is determined is determined by a vector space V and one endomorphism A, where we just say that x times V for an element in V is the same as this endomorphism applied to V. And from then on, you can just say sort of powers of x are just by applying A over and over again, and so on. So this representation or this module structure is uniquely determined by the vector space and the endomorphism. Now it is a well-known result of linear algebra that in a suitable basis we can write our A in Jordan normal form, which means we can write it as a direct sum of Jordan blocks. As J lambda 1 n1, J lambda r nr. And when I'm writing this direct sum of endomorphisms in matrix form, this means the block matrix where I have this block in the first thing, then second block, third block, and so on. In a formal sense, it just means I can decompose my vector space into a direct sum of subspaces where this thing acts on the first subspace, this thing on the second, and so on, and this on the rth subspace. And the Jordan block itself is just an n by n matrix that has lambdas on the diagonal and then ones above the diagonal. So we already have some kind of decomposition. I guess I should at some point also have said that we want this thing to be finite dimensional. Otherwise, this doesn't work at all. Yes. So we have some sort of decomposition into subspaces that are, well, invariant under the action of our module. So they are subspaces. And now the question is, are they simple? And the answer is they are usually not simple.
I mean, if they're block diagonal, they're clearly not simple, right?
No, I mean, on each block, the action just looks like this. Yeah, like this.
Okay.
And that does look simple, but it's not. Or I don't know, maybe it also doesn't look simple. Are the VI simple? And the answer is usually no. More precisely, if they are, yeah, I guess if they are more than one dimensional, they are not simple. For example, if we look at the Jordan block, yeah, I don't know, that V be C2 and consider J of 0 and 2. This means that we have x acting on the vector 0, 1. Sorry. So J0, 2 just looks like this matrix, meaning that x times the vector 1, 0 is just 0, but x acting on 0, 1 is 1, 0. This thing is, well, if you want, it is still in the span of 1, 0. So this means that the space, the span of 1, 0 is an R submodule. Because if you act, yeah, it's a submodule. And on the other hand, if you take any complement to it, then you're going to have some component of 0, 1 in there, which will get mapped to 1, 0. So any complement to that is not an R submodule, and therefore it doesn't decompose, but it, as we just showed, has a non-trivial submodule. And yeah, to be fair, this is the sort of prime example of something that is not simple, something that doesn't decompose, because you're always looking, in representation theory, are the matrices that are used to represent my groups, can they be written as Jordan blocks, or can they be diagonalized? Which means, can they be written as Jordan blocks that are just one thing, just have n equal to 1, so that you just have the eigenvalues on the diagonal and no additional ones. And as soon as you have a Jordan block that is bigger than 1 by 1, you automatically have a representation that is not really decomposable, or that doesn't decompose. Oof. Yeah, now for the
very stupid question again. Does this mean that all simple submodules will be one-dimensional?
No, definitely not.
So what is an example of a two-dimensional simple? Because you said that, like, do you understand my question?
Yeah, I understand your question. Well, the answer would be any two-dimensional representation of any two-dimensional unitary representation, for example.
The VIs could be simple, for example, even if it's two-dimensional. So so when you asked, are the VIs simple, you said probably not, but they could be too. They could be simple.
Yes, if they are one-dimensional in this case, yeah.
But even if they're two-dimensional, it could be simple, right?
Well, not if you're talking about CX modules.
Okay.
For other algebras, sure, there are simple modules that have more than one dimension, or that have dimension more than one. For example, groups.
Yep.
So now for the, I guess, more tractable example, if G is a group, and rho from G to GLV is a representation. which just means a group homomorphism. Then we can make this representation into a CG module structure on V. As follows, we have a general element of CG is some linear combination. And we multiply it by a vector just by saying that it should be this thing here. So we are using the coefficients as coefficients. We are saying, okay, the individual elements of G act on V by means of this representation. And that's it. Can also work backwards just by saying that, well, G is contained in CG, and then we can work backwards and define a representation from it. And that's why we say that complex, at least, representations of G are the same or can be identified with CG modules. And you might notice that this whole language allows me to basically do what Daniel Baumann has always been very, I don't know, bad boy about in quantum field theory. And he said, oh no, I've referred to the representation space as the representation. Yeah, if you want to talk about modules, that's exactly what you do, and mathematically completely fine. I don't know, would you like me to address the other kinds of group algebras, because they also have can be turned, like this structure can also be very nicely defined. I don't know, just one example maybe. We can do G is topological, group then, and row from G to R, no, okay. Locally compact topological group. And we have a continuous representation in GLV, then we can define an L1G module structure on V by having F times V being the integral f of x, rho of x, V d mu x. Now this is a Haar measure. And this thing is an L1G. Similar thing also works for locally compact measures, for locally compactly supported measures, compactly supported distributions, whatever. Sorry, I have to get the light. Better. Secondly, or I guess thirdly, fourthly, if G is a Lie algebra and rho is a Lie algebra representation, then we can turn this representation space into a UG module. By having, well, UG as an algebra is still still generated by all of the objects in the Lie algebra G. So if we define how the Lie algebra acts on our vector space, we can just extend it to the whole universal enveloping algebra. So we can just define what this thing does with vectors, and the answer is, well, just use the representation. So this means that representations of our Lie algebra can be identified with UG modules. And again, we're talking about complex representations. With UG.
Yeah, I actually still haven't understood the difference between a universal enveloping algebra and a Lie algebra.
Okay, a Lie algebra is a vector space with a Lie bracket.
Which is okay.
Yeah, but like you can't multiply elements in a Lie group.
Like
sorry,
you mean tensor multiply?
No, I just mean so if you have a Lie algebra, whatever else. Lie algebra L is a vector space with Lie brackets defined as some multilinear operation or some bilinear operation with Jacobi identity, whatever. So this means that, yeah, this expression is perfectly well defined, just, yeah, the Lie bracket. But if you want to write it like that, like what the fuck is this multiplication supposed to be?
Yeah.
And one thing you could say is, okay, I'll just look at maybe my Lie algebra is contained in some bigger associative algebra. Like, for example, my Lie algebra consists of square matrices, and, well, by coincidence, I know how to multiply square matrices. So maybe I can define multiplication that way.
I feel like this question becomes very like physics oriented too, because I think this is similar to what we are doing when we are going from classical to quantum and things like that too, right? When
how do you mean?
We define the commutator, the Lie bracket as the commutator, right?
Yeah.
Like, where is this definition coming from? That's my basic question. Like,
oh, that definition is coming from the fact that we are always talking about symmetries, and these symmetries are defined by Lie groups, and these Lie groups have Lie algebras. And somehow by this action, by some group action, we get a representation of the Lie algebra on our fields. And the Lie algebra representation, maybe that's where all of this is coming from. The Lie algebra representation is a map from that Lie algebra to the linear maps on some vector space, where we map the Lie bracket of two elements to the commutator.
and in the universal enveloping algebra, this is what you're doing. You're dividing this to get
So the idea is sort of that you're always mapping to associative algebras where you have some kind of product, So ideally, you would like to pull back the product from end v to L, so that you can then actually have some product on your Lie algebra, where you can say, oh yeah, the Lie bracket is just the commutator.
I see. I see.
The problem is that yeah, you want to do it in a sort of most general way, in the most general way, and that turns out to be the universal enveloping algebra, which just turns out to be very high dimensional, just by the fact. Yeah, we're going to talk about this a bit later, but if you have like a creation operator, that is an element of the Lie algebra, and you can apply it infinitely often, and it should never be zero. So all of the powers of this creation operator already are linearly independent, and you have an infinite dimensional vector space.
Vector space. Okay. Yeah, I see the point.
Okay, so slogan: Lie algebra representations can be identified with modules of the universal enveloping algebra. And now we have one small example. The complexified version of the Lie algebra of U1 is just C, with the Lie bracket, where two elements are just sent to 0. Then, just by formally looking at the definition, the universal enveloping algebra of this thing becomes the, well, direct sum of C infinitely many times, modulo the relation that two different, that the product should be commutative. But this is now just the polynomial ring in C, because we can write this as C plus C times X plus C times X squared. You can sort of decompose this as a direct sum where you have all of the powers of X as direct summons. And this shows that, well, representations of U1, complex representations of U1, are complex representations of U1 complexified. Those are modules over the universal enveloping algebra of U1 complexified, which are just CX modules, which in general don't decompose.
Question.
Yeah.
Could we, in the complex polynomial ring, swap the polynomials for a sign expansion, so Fourier expansion, or any other basis?
I'm sorry, can you repeat that?
So could we think of the polynomial ring as, instead of having just, constant x squared, as having a sort of Fourier expansion, or having another polynomial expansion like with Chandra polynomials?
Well, I mean, you can view Fourier expansions as polynomial expansions, or like as power series expansions in e to the I z, right?
Yes.
But the thing is, we're still talking about finite linear combinations and nothing infinite here.
Okay.
Yeah, okay. So you might ask, why is that here the case? Usually you would be used to nice results where every blah, blah, blah representation decomposes. And there indeed exists such a result for the algebras. It's just that this result exists for semisimple Lie algebras. And U1 is abelian and therefore not semisimple. Okay, and the last thing about modules, or the last example of modules, and I think then we're just going to take a break, is that if phi is a linear map, by the way, linear maps in representation theory are usually called entwining maps or intertwining maps. Then the kernel, meaning the elements that get sent to 0, and the image are also, or are submodules of, well, this thing is a submodule of M, and this thing is a submodule of N. Yeah, can be proven very simply. Yeah, and I guess the last thing before the break would be to just notice that the problem of classifying R modules splits into two parts. Namely, is every R module decomposable? And secondly, if that is the case, what do the simple R modules look like? More specifically than just divided by some ideal. And there are some nice theorems for both of these things, and maybe we'll look into them after the break. Okay, I guess we can resume. Okay.
One more question.
Yeah.
Can division only happen through a two-sided ideal?
Okay, so the thing is, you can divide by anything you want, basically. The question is, what would you like to get at the end? For example, we have divided by left-sided ideals too.
Yeah.
Here, basically. Oh, yeah, I guess done that before. And the thing that you get is a left module, but not necessarily a ring anymore. If you want to get a ring, if you divide, you have to divide by a two-sided ideal. This is sort of similar to
A normal
if you
subgroup.
divide G by some subgroup, you still get something that has a G action on it, but not necessarily a group. But if it's a normal subgroup, then you have a group. Okay. Yeah, I call it a lemma. It's maybe a bit bigger than that, so, but still a slightly bigger result, maybe. So if M is a finite dimensional inner product space, so that you can talk about unitarity, and rho from G to UM is a unitary representation. Then the so described CG module M is decomposable. Because if you have a unitary representation, you can just take the orthogonal complement of a submodule, and it's still a submodule. So then you get that like by some induction argument, you get that it's decomposable. Also note that if you don't have a unitary representation, but for example, a finite group or like a compact topological group with a continuous representation, then you can always define another inner product that makes this representation unitary. So you also get this same result under slightly weaker conditions. And secondly, this is what I was already hinting at before the break, that G be a semisimple Lie algebra, then every finite dimensional UG module is decomposable. Semisimple just means that there are no elements that commute with every other element, meaning that there are no elements that have zero Lie bracket with every other element. Well, except this element is zero itself. In other words, it is a Lie group, a Lie algebra whose that is completely determined by its adjoint representation. Okay. And I guess now for the the big result that we can formulate in this very general setting, and it's the one lemma that we always talk about when we have representation theory, namely Schur's lemma. And yeah, there are so many different ways of formulating it, but I've recently seen a very nice formulation which I'm going to pose here, that M and N be two irreducible, two simple R modules. Where R is again an associative C algebra. Let M be finite dimensional. And then we look at the homomorphisms, or the R linear maps between M and N. And they form a vector space, a C vector space. And the dimension of that C vector space is either 1 if M and N are isomorphic, or 0. Would you like me to prove this?
No.
Okay, the proof is quite simple anyway. Mainly relies on the fact that what I've stated before, that kernels and images are again submodules, and hence must be either the whole space or 0. So then you immediately get, if you have a non-zero homomorphism, then you immediately get that this one has to be an isomorphism. And then you can use the usual Schur argument that it has to have an eigenvalue and an eigenvector to see that it must be the multiple of any other homomorphism between those two. And I guess the big takeaway of this is endomorphisms of representations of modules help characterize irreducible representations or simple modules. Jesus. Simple modules. Because they have to act as constants on them. One example, or general examples of this, is the center of an algebra. So the center of R is defined as the elements that commute with every other element. An element of the center then defines an endomorphism of such a module. Of M just by multiplication. The morphism phi. Namely, we have phi of b times x is equal to a bx, but now a and b commute, so this is the same as bax is the same as b of phi of x. So we are able to pull out this coefficient outside. So phi is indeed an endomorphism of M, and therefore it acts as a constant on simple subspace or on simple submodules. I guess we can now have a look at what the centers of our various rings look like. First thing, we'll see some polynomial ring is just commutative, so it is equal to its own center. So every element acts just as a constant on every simple module, which, yeah, makes sense. We've seen that simple modules are just one-dimensional. Yeah. And I mean, you can only act on a one-dimensional vector space linearly by multiplication with a constant. Yeah, now I guess the more interesting example is if G is a finite group. That A be in the center of CG. Sorry, not C, Z. Let's say is equal to FG G for all with the sum over all elements G in the group. This is just the most general expansion. Then if we want this thing to commute with every element in the algebra, this is the same as having it commute with every element in G. So if we want AH is equal to HA, this is the same as having A being equal to HA, H inverse, so we just have to conjugate with H, which means that we can pull out the coefficient, and then we have HG, H inverse. Or we can do sort of a substitution inside the sum and say this should be the same as this thing here. And well, we want this to equal A, so it should be the same as FGG. So this shows that our coefficients, or I guess F, is constant on conjugation classes. In other words, F is a class function. And from the theory of characters, I think it is established that all of the characters span the class functions, or that the set of class functions is spanned by the characters of the irreducible representations. So in fact, our class functions characterize our irreducible representations uniquely, or not uniquely, but completely. But I could be wrong about this. Well, at least finite dimensional ones, I guess, characterize finite dimensional irreducible representations. Secondly, if we have a Lie algebra, we can define what's called a Casimir element, or no, that's not true. The elements of the center of the universal enveloping algebra are called Casimir elements. In the case of this Lie algebra being SU2, for example, this one of those Casimir elements would be, for example, the total angular momentum. Yeah, I think I've also put down a construction here. So, for example, if x1 till xr is a basis of G, just a C vector space basis, then take its dual basis, y1 till yr with respect to the killing form, which is just some scalar product that is defined on G. Or in particular, it's a scalar product if G is semi-simple. So I guess we have to assume that G is semi-simple here. And then we can just define the sum of xi, yi to be pi, and this is one very famous Casimir element And for example, if we are talking about the Lie algebra of SO3 or SU2, this would just be the sum multiple of the total angular momentum.
In this case, would this Casimir element be metric dependent?
It depends on the killing form, and the killing form can be defined without any kind of metric. Killing form is the trace of the adjoint x times adjoint y, where you interpret x and y to act on the vector space G as linear maps, and then you can multiply these linear maps, and then you can take the trace, and that is the killing form of x and y.
Okay. Will you be talking about this later? Like,
No.
okay.
Just a side note. All right, I'm not sure. Maybe I will mention the killing form. But I guess this also depends on how much you still want to hear, because I now have a bit of a thing of how to construct irreducible representations of Lie algebras in general.
I mean,
of them.
by later I meant like in future classes.
Oh, no, this is not going to come up anymore.
Okay.
Okay, but would you like to do some more stuff about, or like, would you like to construct the irreducible representations of Lie algebras now, or would you like to finish? No opinions?
Even I would like it actually.
Somehow I lost the chat. Where the fuck is the chat? Why can't I open the chat? Ugh, seriously. Okay. Okay, so what you do for Lie algebras, okay, we now suppose that G is a semisimple Lie algebra, which has firstly the advantage that all of the representations are decomposable. Secondly, the killing form is an actual scalar product. And thirdly, or at least is doesn't have to be positive definite, I think, but is a scalar product, something like that. And thirdly, all of the information is contained in the adjoint representation. And what we are doing now is, or what is usually done, we are fixing a maximal abelian sub algebra. Oh God. Yeah, I think I'm stop using Fraktur letters from now on. H, called a carton sub algebra. Abelian just means that x and the Lie bracket of x and y is 0 for x and y in H. And the idea is that since, well, they all commute, they can be diagonalized, or more particular, since they all have Lie bracket 0, all of their adjoint actions also commute. Adjoint action is just, if I apply it to y, it's just the Lie bracket of x and y. So in particular, they can all be diagonalized simultaneously. And this means that, well, I don't get eigenvectors, I get something much better. I don't get an eigenspace decomposition, I get what's called a root space decomposition. Namely, the Lie algebra G decomposes into H plus, and then a direct sum over all roots of G lambda, and I'm going to define what G lambda is. G lambda consists of those vectors, or those x and g, such that for all element y in H, commutator of y with x is equal to lambda of y times x. So we are saying this is the eigenspace with eigenvalue lambda y of add y for all y in H. Usually we have our Cartan sub algebra generated by finitely many elements. For example, if we are talking about SO3, it's usually like the generated by the angular momentum in z direction. And then you just have the eigenspaces there. Or I guess usually you go for total angular momentum and then angular momentum in z direction. But since total angular momentum isn't an element of the Lie algebra, we don't do that here. So this is just something that happens if you diagonalize multiple things simultaneously. You don't get eigenspaces, you even get root spaces. And these roots that sort of characterize the eigenvalues are linear maps from H to C, just because this Lie bracket is linear in its first argument. Linear because it's bilinear. And yeah, in particular, we call, of course, there's not, of course, those root spaces are not all different from 0. Just because you have a finite dimensional vector space and you only have finitely many roots, just as when you just diagonalize one matrix, you only have finitely many eigenvalues. So we call the collection of all of those roots, call them the roots. Maybe I should call them. Yeah, I think they're called delta, not lambda. And these roots form a very interesting algebraic structure, or not algebraic, geometric structure, namely that of a root space. And you can draw it very nicely because usually this H is low dimensional. So its dual has the same dimension. And yeah, you can just draw them. For example, a famous root system is this one. Or this one. Or this one. Yeah, I don't know. Those are things you can classify. And this is where those Dinkin diagram classification of all of the simple Lie algebras comes from. Yeah, maybe a bit more to the point is the fact that you usually decompose your root system as a set of positive roots and a set of negative roots, which is a choice, an arbitrary choice. But it has to sort of be done using one plane. For example, if we have this root system consisting of these 6 roots, where you can sort of choose to draw your separating plane here and call these 3 roots positive and these 3 roots negative, and that's it. Well, whatever. And yeah, more to the point, if we now have a UG, a UG module, then we can also decompose this module, but now they are called weight spaces. Just because, yeah, you can again diagonalize the action in a nice way. Or again, like your Cartan Sub Algebra, still these operators still commute as operators on your module, or as endomorphisms of your module. So then you can diagonalize them simultaneously and you can do the same decomposition. Composition M is equal to direct sum lambda of M lambda, where M lambda is the set of all vectors such that for all y and h we have yv is equal to lambda yv. And well, now we have this decomposition of our module and also our decomposition of the original Lie algebra. So you might ask, how do these work together? And we have if lambda and mu are any element of the dual space of H, then if we multiply any element in the lambda root space with an element of the mu weight space, we get an element of the mu plus lambda weight space. So we basically add eigenvalues, or put differently, this weight space decomposition sort of classifies our vectors with respect to the eigenvalues that they have when you apply elements of our Cartan sub algebra. And what these elements of the positive and the negative root spaces do is that they increase these eigenvalues or they decrease these eigenvalues with respect to an arbitrary notion of increasing and decreasing. But they sort of change these eigenvalues and we designate one direction as to be increasing them. And yeah. So the positive root spaces are what we could call raising operators or creation operators. Or no, that's maybe a bit too on the nose, but raising operators. And for the negative roots are lowering operators. And if M is a UG module, we call some weight lambda to be the highest weight of M if sort of for all larger weights the weight space is 0. Oh yeah, okay, maybe I should have introduced something. Okay, maybe forgot this general terminology. The elements of the dual space of H are called weights, and the ones that have a non-zero root space associated to them are called roots. And now we have some notion of positivity and negativity for roots. And the question is, can we also talk about positive and negative weights? And yes, we can. Say lambda and H is positive or dominant if, well, the killing form or the scalar product of lambda is non-negative for all positive roots. And this thing is just the dual scalar product induced by the killing form. For all positive roots. for all dominant mu. Okay, if we have this diagram here, maybe I erase whatever we call positive and negative. We can now also ask, what are the dominant things here? And the dominant weights, well, they are sort of bounded by this line and by this line. So here we have dominant weights. Just because, well, this line is this line here is orthogonal. Jesus, this line is orthogonal to the rightmost root, and the other line is orthogonal to the leftmost root. Okay, we have a highest weight, the notion of a highest weight, and it's quite simple or quite easy to prove that every simple UG module firstly has a highest weight just because it's finite dimensional. If it didn't have a highest weight, then it would sort of have infinitely many non-zero weight spaces. So it would be infinite dimensional. And secondly, because it's simple, this highest weight space can't be zero, can't be spanned by multiple things. As a highest weight lambda, with m lambda being one-dimensional. And then we have m is, well, generated by this one element as a UG module. And I guess using the comment I made earlier, that we can now just retrieve m as being UG divided by the annihilator of V, we can ask ourselves, well, what does this annihilator ideal look like? And, well, the elements of V gets annihilated by what? Firstly, it gets annihilated by all of the positive root vectors, sort of because your weight is already the highest it can be. So if you try to increase the weight, you can't do it, you get zero. So for a positive root, we have x in that root space. Then we have x times v is 0, because we can't increase the weight any further. And secondly, well, we know that it's in this weight space. So we have for any element of our carton Sub algebra, we have y times v is equal to lambda of y times v. So in other words, y minus lambda y, v is also 0. And that turns out to be everything. So this is the ideal generated by x in, or by the elements of the positive root spaces. And by relations of the kind y minus lambda y for y in the carton Sub algebra. And conversely, if lambda
how do you exactly define y minus lambda y? Lambda y would be a matrix representation here, and y would be a...
No, lambda y is just a number.
Okay, a number. Okay, I see.
So what we have is this thing is in G, this thing is in C. So their sum would be in, well, definitely in the universal enveloping algebra.
Okay.
And conversely, for any lambda in, for any weight lambda, we could define the ideal I lambda to be, well, exactly that. X, Jesus. And y minus lambda y for y in H. And then, well, this is an ideal, a left UG ideal. So UG submodule, and then this would be a UG module. And it would be generated by a single element, namely generated by 1. So it would be an irreducible one or a simple one. So this means that every finite dimensional irreducible, or every finite dimensional simple UG module is given by UG modulo such an ideal. And on the other hand, those produce all of the irreducible ones, or all of the simple ones. Now this is all very abstract, I guess. So I will talk about an example. And of course, it's the one example that is always talked about when we talk about the representation theory of Lie algebras, namely G equal to SL2C. We can write it in terms of 3 generators, and I'm going to use the mathematician notation. Sorry. It is generated by the 3 elements x, y, and h, where we have the following Lie brackets. We have x and h, no, h and x is equal to 2x, h and y is minus 2i, 2y, and x and y is H. Then we choose the span of H as the Cartan subalgebra. And well, the space of weights is then just isomorphic to the complex numbers. From here we see that, well, X is an eigenvector with eigenvalue 2, and Y is an eigenvector of eigenvalue -2 of at H. So that means that our root space consists of the elements 2 and -2, where the root space of 2 is generated by X, and the root space of -2 is generated by Y. Then I didn't mention that before, but you can define integral weights, and when a weight is integral and dominant, then this representation constructed here is actually finite dimensional. So lambda, in this case, lambda is integral if, well, lambda is an integer, which is ultimately where the word, why it's called integral. Now we can choose a decomposition into positive and negative roots. And of course, I'm going to say that 2 is positive. Then a weight is dominant. Well, if it's scalar product, i.e. its product with 2 is positive, so, well, if it is positive, and, well, if we now want to find our finite dimensional representations, well, we have to take a non-negative integer number. So for n and n naught, I guess, we have we call our representation Vn, or our module Vn. This is just u divided by, and now this giant ideal just boils down to, well, we want X to make it vanish, because if we say that the positive root space is spanned by X, we are saying that X is our creation operator, whereas Y is our annihilation operator. So we say, okay, we try to, if we have already the maximum number of particles, when we apply the creation operator, we just it just vanishes. And the second condition is that, well, H, the number operator, or not the number operator, but H should act as n, just as the natural number n. Okay, then 1 is the highest weight vector. And now we can get all the other vectors in this module by successively applying Y. So define Vi by having by applying y I times to 1. Then on one hand we have, well, y applied to vi is equal to vi plus 1. On the other hand, you can also ask, what is h applied to vi? And yeah, basic calculation shows that this is equal to n minus 2i times vi. And lastly, can apply x to vi, and this is, well, big expression, but ultimately in minus I times I minus 1 vi minus 1. So if you ignore those coefficients here for a moment, yeah, this does look like creation operator, annihilation operator, sorry, here, like creation, annihilation operator, and here something number operator. Or I guess more accurately, if we are talking about angular momentum, which we really should do here, is we have the L plus, the L minus, and here we have the LZ. And
what is Vn again?
Vn
Yeah.
is this representation space, or this quotient module that we define it.
But can't we define similar annihilation creation even in the original module without the division? The highest weight
sure.
representation.
The thing is just those relations wouldn't hold.
Like you would have different relations, but it would be like similar, right?
No, because the only reason why, for example, h times v0 is equal to n is that we literally say that h should act as n.
Okay.
Okay, bye, Liam. Otherwise, we would just have the relations of the Lie algebra here and nothing more. And this means especially that, like, we never stop creating elements. Like this creation thing would never stop.
Stop. Okay.
So then we wouldn't have a highest weight. You could also want that, sure.
No, but I thought the highest weight existed a priori to the division.
No, we choose it here.
If you go up slightly,
yes,
so,
at some point I say every simple module has a highest weight. Every finite dimensional simple module has a highest weight.
Okay.
And
so
the reason, yeah.
So what we did is we created a simple module by the division.
Yes.
Okay, I see.
And in fact, these are all the simple modules. They are all uniquely classified by this n, which, if you rescale everything, means that every irreducible representation of your rotation algebra is uniquely determined by the angular momentum, or the total angular momentum.
Yeah.
Or I guess spin.
Spin.
Is there something else? Yes. Also note that if we have, I think, Vn plus 1, and we apply x to it, no, firstly, h times Vn plus 1 is equal to minus n minus 2 times Vn plus 1. Okay, I don't know. Important takeaway, I guess, is that Vn plus 1 is equal to 0. Forgot how to prove this. But this basically shows that Vn is generated by, or even has a basis consisting of V0 until Vn. And where this thing has, when you apply h to it, has n, and this thing has, when you apply h to it, minus n. So what our x and y do is that they, yeah, I mean, we've already talked about this. They increase and they decrease the h eigenvalue by 2. And if we now say L3 is h divided by 2, L plus is x, L minus is y, I guess there are probably some i's flying about the place. Then and we rescale it, yields exactly the angular momentum early algebra, or algebra we called it, just by virtue of, well, SO3 being isomorphic to SU2, and then when we complexify it, we get SL2, and that is the thing we're looking at here. Yeah, and I think that was everything. Are there any questions?
We were talking about finite groups, right? How did we suddenly come to SU2?
We've finite groups. It was ages ago. That was here.
No. I'm asking you, like, the final result, when we said that we have a highest weight representation.
Yeah.
But that's only for finite groups, right?
Oh no, that is for finite dimensional representations of our semisimple Lie algebra.
Okay. Yeah, makes sense.